Okay, in this video we're going to do pages 20, 21, 22, 23, and 24 in your big Chapter 2 notes packet. So here we go. Overview, we're going to use calculus to optimize a solution. Okay, so that's the terminology we're going to be using. In these types of problems, some quantity must be either minimized or maximized. You will have the same approach whether you are looking for a max or a min, so do not get confused about this. Make sure you are actually answering the question. Not doing so is a common error. Use your curve sketching technique from 2.3 and 2.4, i.e. first and second derivative test with concluding statement resulting graph of original function. Okay, so we're probably not going to be doing the resultant graph of the original function, but we'll get to that in just a second. So here's your first example. Example 1, find the minimum value of the functions. We're looking for a minimum value. So there's my function. I'm going to take my first derivative, and when I take my first derivative, I'm going to get 3x squared minus 15x plus 12. Okay, I'm going to go ahead and take my second derivative as well, and I get 6x minus 15. Okay, so now what I'm going to do is I'm going to factor my first derivative first by factoring out a 3. X squared minus 5x plus 4. This is going to make your problem a lot simpler. Next, now do your factoring inside. So you should be getting x minus 4, x minus 1. All right, so what are your critical values? You should say that the critical values are 1 and 4. So now let's test them. Okay, so if I put 0 into my first derivative, I'm going to end up getting 3 times negative 4 times negative 1, which will be a positive. Then if I put 2 in, I'm going to get 3 times a negative 2 times a positive. So that's going to be a negative. And then if I put a 5 in, I'll get a positive times a positive times a positive. So what does this look like? This is what this looks like so far. Let's do the second derivative. What if I plug in a 1? I get 6 minus 15, which is going to be negative, so that affirms what I'm seeing. And then plug in a 4, I get 24 minus 15, which is going to be a positive, so that is good as well. Okay, so let me just scoot this up a little bit. All right, so what am I seeing? I need to first off figure out what I'm looking for. Okay, so in the interest of space, maybe I'll put my statement up here. So what I'm seeing is basically at CV equals 1, the slope changes from positive to negative, which gives me a max. At CV equals 4, the slope changes from negative to positive, which gives me a min, and that's what I'm looking for. Okay, so that's the first derivative statement. My second derivative statement would be as follows. At CV1, f prime prime of 1 is less than 0, and that's going to give me what? A concave down, which is a max. So at CV of 4, f prime prime of 4 is greater than 0, which makes it concave up, which leads to a min. So my min happens at 4, okay, so that's good to know, but I need to find the minimum value. So what I'm going to do is I'm going to put in f of 4, and when you plug it in, you should get a minimum value of 12, and that would be your answer. Okay, so this is page 20. Let's look at 21 now. 21 says find the maximum quantity of this given this. So here we have two variables. So the first thing we have to do is use our constraint. So initially I have q equals x times y, and x plus y equals 4. So I know that y equals 4 minus x. Okay, so therefore q, the new and improved objective function, is going to be x times 4 minus x. So q is going to be 4x minus x squared. So q prime is going to be 4 minus 2x. And q prime prime is going to be negative 2. Okay, which is going to be negative, so that's going to give me a max, which is what I want. So that's good. Okay, so now what I want to do is take my first derivative, set it equal to 0, and I'm getting x equals 2. Okay, if I plug in a 0 into my first derivative, I get 4 minus 0, which is a positive. If I plug in a 3, I'm going to get a negative. I see the function is always going to be concave down. So therefore, this is the shape, and I do get a max at 2. So at CV of 2, slope changes positive to negative. That gives me a max. At CV of 2, f prime prime of 2 is less than 0. That makes it concave down, which gives me a max. All right, so I still need to find the q. So far I know that x is 2. And since x plus y equals 4, y also has to be 2. And therefore the product of 2 times 2 is going to give me 4. And that's really what I need to have for my answer. Okay? So see if that makes sense to you. So let's go on. This was 21. Let's go on to 22. Okay, so here we formally introduce the terminology of objective function and constraint. I've really been doing this all along, but now what we're going to do is we're going to create our own problem. So steps needed: identify an objective function, what you want to max or min, and sketch if possible. Step 2, identify a constraint, what limits you. Step 3, if necessary, use your constraint to present your objective in only one variable. 4, use this new objective function to conduct an optimization. 5, set up your Sine Chart and analyze the CV. 6, sketch the problem using the Sine Chart for the new objective function. And 7, make certain to answer the questions. Okay, so find the dimensions of the rectangular garden of greatest area that can be fenced off using 300 meters of fencing. Okay, so find what? The rectangular garden of greatest area. So we need area, and if I was to sketch it, it's a rectangular of greatest area. So I'm going to make this my y and this my x. So that area is going to be x times y. Okay. It's going to be fenced off using 300 meters of fencing. So that means that 2y plus 2x will equal 300. Y plus x therefore equals 150. Okay, so I can create a new objective function. So why don't I replace the y with, let's see, with 150 minus x. Okay, so my first thing is going to be to multiply this out. 150x minus x squared. Take my derivative. 150 minus 2x. Take my second derivative. Minus 2. Therefore, it's always going to be concave down. So that will give me a max. And set equal to 0. My x equals 75. Okay, so I wanted to do a little sine chart. So why don't I do it over here? And so that's going to be 75. If I plug in 0 into my first derivative, that's going to be positive. If I plug in 80, that's going to be negative. And I already know that this is negative. So therefore, my curve looks like that, and I am getting a maximum. So they want the dimensions. So you should write a statement as well. So I'm not going to do that this time. But so say here you would write your little statement. We've gone over this numerous times, so I think I can leave that for you. But let's make sure we answer the question. So we want the dimensions. So when I took my first derivative, I found that x is 75. And what I see is, since y plus x equals 150, I end up getting that y also equals 75. And these are both in feet. Oh, no, excuse me, these are both in meters. Let me change both of those. Okay, so these are meters, because if I give you units, give them back to me in the final answer. So what are your dimensions? 75 meters times 75 meters. And so that means that the optimal size is going to be a square. Okay, so we've done this type of problem before, and the challenge is you've got to create your own equations. Okay, so that brings us to the next page, which should be 23, I believe. Yes. Okay, so let's go to 23 and we'll read that. Okay, so this one says, a rectangular garden of area 75 square feet is to be surrounded on 3 sides by a brick wall costing $10 per foot, and on one side by a fence costing $5 per foot. Find the dimensions of the garden such that the cost of the material is minimized. Okay, so what's my constraint? I know that my area has to be 75. So 75 has to equal x times y. Okay, that's my constraint. So let me think about this garden. So look what I have. If this is going to be my y, and this is going to be my x, this is y, this is x. Now, the rectangular garden is to be surrounded on 3 sides by a brick wall. So if this is going to be the brick wall here, right, so let's just say that that is your brick wall, then that means I can put a price of 5y, 5x there. And then on the other side is by a fence that's going to cost, so I'm sorry, hang on 1 second. I read that incorrectly. The brick wall is going to be 10, 10, and 10. And the fence is going to be 5. Okay, so what do I know? So let's see what I can figure out from there. So I know my area is going to be length times width. And so therefore, don't I know that, how about if I say 75 divided by what? How about divided by y equals x? Okay, so my objective function initially is going to be the cost. It will add up to, let's see, we have 10y and 10y, so that's 20y plus 15x. Okay, so the problem is I have two variables. So let's replace the x, and we'll have everything in terms of y. So my new objective function is going to be cost equals 20y plus 15 times 75 over y. Okay, so how does that go? So let's continue. Cost is going to equal 20y plus, 15 times 75 is what? 1125, and then bring this y up. Now take your derivative. So you're going to have 20 minus 1125 y to the negative squared. And c prime is going to be positive 2, let me just make that better. 2250 over y to the third. Okay, so as long as my y is a positive number, which it has to be, right, then I know I'm going to minimize the cost by this optimization process. So notice that when you have this negative power, it's great for taking derivatives, but it's not clear what that means when we're trying to analyze it. So let's write it like this instead. 20 minus 1125 over y squared. Set that equal to 0. We get 20 equals 1125 y squared. Do your cross products. 20y squared equals 1125. Divide by 20, divide by 20. Y squared equals 1125 over 20. Okay, so now we're going to get our calculator out. And so if I have 1125 divided by 20, and then I'm going to take the square root of that, I end up getting a y equal to 75. Equal to 7.5. Go back again. So that's going to be 7.5. And what are my units? Feet. Okay, so if my y is 7.5 and 75 equals xy, then my x has to be 75 divided by 7.5, which makes x 10 feet. Okay, so it says, find the dimensions of the garden such that the cost of the material is minimized. So it looks like I'm going to have my dimensions will be 7.5, and that's going to be the y, by 10, and that's going to be the x. Okay, those are my dimensions. Now, I could also ask you about the costs, so you can really answer lots of questions. Okay, so I didn't do a sine chart, so let's do that now. So since I solved for my y, I'm going to put the y on my sine chart. And what I see, if I plug into my first derivative, then what will I get? If I plug in that, let's see, it's going to be, well, I already know that this is going to be this, right? So it has to be a min. So therefore, this has to be negative, and that's going to be positive. Okay, so that's what's going to look like. And then you would write a little statement here. And then you're good to go. But your final answer would be these dimensions. Okay, and I think we have one more to do on page 24. So let's do that next. Okay, so this is kind of a complicated one, but it's also kind of a neat one. Okay, a canvas wind shelter for the beach has a back, 2 square sides, and a top. Find the dimensions for which the volume will be 250 cubic feet. And that requires the least possible amount of canvas. So you want to have the least possible amount of canvas. That's your objective. So you're going to minimize. The least possible is minimizing. So your objective function actually deals with the surface area. So look at your different surface areas. Okay, the top surface is going to be x times y. The side panels will be x squared. And then what will be the back panel? That's going to be another x times y. And your constraint has to be the volume. So the volume equals length times width times height. And that has to equal 250. Okay, so now we have to, let's clean up my surface area here. So I really have 2xy plus 2x squared. Okay, so it looks to me like I want to replace that y. So what I see is my volume really equals x squared times y, and that has to equal 250. So what I'm finding is that y equals 250 over x squared. Okay, so here's your new objective function. Surface area is my objective, and it's going to be 2x times y, and y is 250 over x squared, and then plus 2x squared. Okay, so this x cancels that power, so I can rewrite this now as 2 times 250 is 500 x to the negative 1 plus 2x squared. Surface area prime equals negative 500 x to the negative 2 plus 4x. Okay, so, and let's go ahead. We might as well take the next derivative. That is going to be a negative 2 times that will be a positive 1,000 over x cubed, and that's always going to be positive because x has to be positive. So therefore, I do indeed have a minimization because that's what they wanted, right? Requires the least possible amount of canvas. Yes, so it's going to be a minimization. Okay, so good. So let's get an x value. So if you're going to set this equal to 0, it's going to be much better if you make the x negative 2 x squared, and that's going to equal 4x. Do your cross products. 4x cubed equals 500. So 500 divided by 4 equals 125. X cubed is going to 125. So x is going to be 5. Now, is that 5 feet? Yes, it is. So x will be 5 feet. So, if x is 5 feet, what is y? Well, y is going to be 250 over 5 squared. So it looks like y is going to be 10. So what are my dimensions? Your dimensions are going to be 5 times 5 times 10. And is that what they asked you for? Yes, that's what they're asking you for. So 5 times 5 times 10 are your dimensions. And that's the last problem.